3 million light-years away, a galaxy spins so fast it should tear itself apart. The Triangulum Galaxy harbors star nurseries that birth suns 100 times more massive than ours. We'll witness blue giants that burn through their fuel in mere millions of years. Explore pink nebulae, where stars are dying in cosmic cocoons, and discover rogue black holes wandering through spiral arms like cosmic predators. Prepare yourselves. We begin. The Triangulum Galaxy spins like a cosmic hurricane that should have destroyed itself billions of years ago. Every night, astronomers point their telescopes toward the constellation Triangulum and witness something impossible. This spiral galaxy, officially cataloged as Messier 33, rotates at speeds that violate everything we know about orbital mechanics. The outer regions move so fast, they should fling themselves into the void like water droplets flying off a spinning wheel. Yet here it stands, defiant. The galaxy stretches 60,000 light-years across, containing 40 billion stars arranged in perfect spiral arms. These arms sweep through space in an elegant dance. But the physics behind this dance makes no sense. According to Newton's laws, objects farther from the center should move slower, just like planets in our solar system. Mercury races around the Sun, while distant Neptune crawls along its orbit. But Triangulum breaks these rules. Stars at the galaxy's edge move just as fast as those closer to the center. Some regions even accelerate as they get farther out. It's like watching a merry-go-round where the horses on the outer rim gallop faster than those near the center. The centrifugal force should tear the galaxy apart, scattering its stars across the cosmos like cosmic shrapnel. The mystery deepens when we measure the galaxy's mass. All the visible matter, every star and gas cloud we can detect accounts for only 10% of the gravitational pull needed to hold this spinning monster together. The remaining 90% comes from something invisible, something that doesn't interact with light or ordinary matter. We call it dark matter. This ghostly substance forms an invisible scaffolding around the galaxy, its gravitational grip preventing the spiral arms from flying apart. Dark matter outweighs all the visible stars 5 to 1. Yet, we can only detect it through its gravitational effects. It's like trying to understand a dance by watching the shadows on the wall. The implications stagger the mind. If dark matter exists throughout the universe, then everything we see, every star and planet and galaxy, represents just a tiny fraction of reality. We're like inhabitants of a vast city who can only see the streetlights, unaware of the massive buildings that surround us. The Triangulum Galaxy has been spinning this impossible dance for over 10 billion years. Generation after generation of stars have lived and died while this cosmic puzzle has remained unsolved. Each rotation takes 200 million years to complete. And in that time, countless civilizations could have risen and fallen on worlds orbiting its 40 billion suns. But this spinning mystery is just the beginning of our journey. Deep within those spiral arms, something even more extraordinary awaits us. Deep within the Triangulum Galaxy's spiral arms, cosmic nurseries are giving birth to monsters. The largest star-forming region in the galaxy, known as NGC 604, glows with the intensity of 600,000 suns. This stellar maternity ward spans over 1,000 light-years, making it 40 times larger than the Orion Nebula that decorates our night sky. Within this churning cauldron of gas and dust, gravitational forces are sculpting stars so massive they dwarf our sun like mountains dwarf pebbles. The process begins in silence and darkness. Vast clouds of hydrogen gas, each containing enough material to build 1 million solar systems, drift through space at temperatures just above absolute zero. These molecular clouds are the raw materials of creation. Invisible to our eyes, but dense enough to block the light of background stars. Then something triggers the collapse. Perhaps a nearby supernova sends shock waves rippling through the cloud. Or maybe 2 gas clouds collide in a cosmic traffic accident. Whatever the cause, gravity takes hold with crushing inevitability. The cloud begins to contract slowly at first, then faster as its own gravity strengthens. What started as a gentle drift becomes a headlong plunge toward the center. As the gas compresses, it heats up like air in a bicycle pump. The temperature climbs from near absolute zero to thousands of degrees. The cloud fragments into smaller pockets, each destined to become a star. But in the dense heart of NGC 604, some fragments gather so much material they become true giants. These stellar behemoths contain 50, 70, even 100 times more mass than our Sun. They burn with temperatures exceeding 40,000 degrees, making them 50,000 times brighter than the star that warms our Earth. Their surfaces glow brilliant blue-white. Hot, they ionize the surrounding gas and paint the nebula in shades of electric pink and turquoise. The most massive stars in Triangulum are living on borrowed time. While our Sun will burn steadily for 10 billion years, these giants exhaust their nuclear fuel in just a few million years. They're like cosmic Roman candles, burning brilliantly but briefly before exploding in spectacular supernovas that can outshine entire galaxies. The irony is profound. The most massive stars, the ones that seem most powerful and enduring, are actually the most fragile. They burn through their hydrogen fuel so quickly that they barely have time to develop planetary systems before they die. Any worlds that might form around these giants would be sterilized by radiation long before life could take hold. Yet, their deaths are not meaningless. When these giants explode, they forge heavy elements in their cores and scatter them across the galaxy. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in the nuclear furnaces of dying stars. But even these stellar giants pale in comparison to the dark predators that hunt between the spiral arms. Between the glowing spiral arms of Triangulum, invisible hunters drift through the darkness like cosmic sharks. These rogue black holes were born from the deaths of the most massive stars. But unlike their siblings that remain anchored in binary systems, these wanderers have been kicked out of their birthplaces. The violent asymmetry of their formation when a star's core collapsed in an uneven supernova explosion sent them careening through space at speeds reaching thousands of kilometers per second. Now they roam the galaxy alone. Each one a gravitational monster with a mass of dozens of suns, compressed into a sphere smaller than a city. They're completely invisible, detectable only when they devour something in their path. Most of the time they glide through the near vacuum of interstellar space, as silent and deadly as submarines in the deep ocean. The Triangulum Galaxy likely harbors millions of these stellar mass black holes, the graveyard remnants of ancient star-forming epochs. Some formed when the galaxy was young and metal-poor, creating black holes with different properties than those born today. Others are refugees from galactic mergers flung into wandering orbits when their host galaxies were torn apart by tidal forces. When a rogue black hole encounters a star, the results can be catastrophic. The black hole's gravity creates tidal forces that stretch and squeeze the star like a cosmic stress ball. If the star ventures too close, it crosses the event horizon and vanishes forever, adding its mass to the black hole's growing bulk. But if it maintains just the right distance, the black hole strips away the star's outer layers in a process called tidal disruption. These stellar cannibalization events create some of the most energetic phenomena in the universe. As the torn matter spirals into the black hole, it forms an accretion disk that glows with temperatures exceeding millions of degrees. The disk launches jets of plasma at nearly the speed of light, creating beacons that can be seen from billions of light years away. The most dangerous rogues are the ones we can't see coming. Unlike active black holes surrounded by glowing accretion disks, a solitary wanderer produces no light signature. It's like trying to spot a black cat in a coal mine. The only warning would come from gravitational lensing. The way the black hole's gravity bends the light of background stars like a cosmic magnifying glass. For any planetary system in the path of a rogue black hole, the encounter would be apocalyptic. The black hole wouldn't need to directly hit a planet to destroy it. Its gravity would disrupt planetary orbits, potentially flinging worlds into interstellar space or sending them crashing into their parent stars. The tidal forces alone could trigger massive earthquakes and volcanic eruptions that would reshape entire worlds. The most chilling aspect of these cosmic predators is their longevity. While stars burn out and galaxies evolve, black holes persist virtually forever. They'll still be wandering the cosmos long after the last star has died and the universe has grown cold and dark. In the far future, they may be the only active players in a dead universe, occasionally finding each other in the darkness and merging in collisions that shake the fabric of space-time itself. But not all of Triangulum's wonders are hidden in darkness. In the galaxy's star-forming regions, celestial artists are painting masterpieces in light. Scattered throughout Triangulum's spiral arms, delicate pink veils mark the final breath of dying stars. These glowing clouds, called planetary nebula, have nothing to do with planets. The name came from 18th century astronomers who thought they looked like distant worlds through their primitive telescopes. In reality, each nebula is a stellar death shroud, the outer layers of a sun-like star blown into space during its final moments. The process begins when a star exhausts the nuclear fuel in its core. For billions of years, the star has maintained a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. But when the fuel runs out, gravity wins. The core collapses and heats up while the star's outer layers expand and cool, transforming the once stable star into a blooded red giant. As the red giant phase continues, the star becomes increasingly unstable. Thermal pulses deep in its core send shock waves rippling through the stellar atmosphere. These pulses blow off the star's outer layers in a series of gentle puffs like cosmic smoke rings expanding into space. The ejected material forms a hollow shell around the dying star. Initially invisible in the cold darkness, then comes the transformation that creates the beauty we see. The star's core, now exposed as a white dwarf, burns at temperatures exceeding 100,000 degrees. The stellar ember floods the expanding shell with ultraviolet radiation so intense it strips electrons from atoms in the surrounding gas. The ionized hydrogen glows red while oxygen emits green and blue light. The result is a cosmic stained glass window painted in impossible colors. Each planetary nebula tells a unique story of stellar death. Some form perfect spheres, their gas expanding uniformly in all directions. Others create intricate patterns, hourglass shapes, or butterfly wings sculpted by magnetic fields and companion stars. The most complex nebula resemble cosmic flowers with delicate petals of glowing gas arranged in symmetrical patterns that rival any artwork created by human hands. The timescales involved are both vast and fleeting. The dying star took billions of years to reach this point, burning steadily through most of the universe's history. But the planetary nebula phase lasts only tens of thousands of years, a cosmic blink of an eye. The expanding shell gradually disperses into the interstellar medium, enriching the galaxy with heavy elements forged in the star's core. These elements become the building blocks for future generations of stars and planets. The carbon in our DNA, the nitrogen in our atmosphere, the phosphorus in our bones, all were created in the nuclear furnaces of dying stars and distributed through planetary nebula. We are literally made of star stuff. Recycled cosmic material that once glowed in nebula like these. The white dwarf at the nebula's center will continue to shine for trillions of years, slowly cooling from white hot to red to brown to black. It's a preview of our own sun's fate, destined to follow the same path when it exhausts its fuel 5 billion years from now. Our sun will swell into a red giant, engulf the inner planets, and then cast off its outer layers in a final act of cosmic artistry. But while some stars die with gentle beauty, others choose a more violent end, one that can outshine entire galaxies in a single moment of stellar rage. In the heart of Triangulum's most active star-forming regions, blue supergiants burn like cosmic torches, racing toward their own destruction. These stellar giants represent the ultimate paradox of stellar evolution. They're the most massive, most luminous, and most spectacular stars in the galaxy. Yet, they live the shortest lives. a blue supergiant burns through its nuclear fuel like a Formula One car burning rubber, converting 4 million tons of matter into energy every second. The nuclear furnace in its core reaches temperatures of 50 million deg, hot enough to fuse elements all the way up to iron. The star's surface temperature exceeds 40,000 degrees, nearly 7 times hotter than our sun. This extreme heat gives the star its characteristic blue-white color and makes it shine with the brightness of 100,000 suns. The stellar wind it produces is so powerful it strips away material at rates that would completely evaporate our sun in just a few million years. These giants are essentially living on borrowed time from the moment they ignite. While our sun will burn steadily for 10 billion years, a blue supergiant exhausts its hydrogen fuel in just 3 to 5 million years. It's like comparing a sip of water to a fire hose. Both drawn from the same reservoir, but consumed at vastly different rates. The star's death throes begin in its core, where nuclear fusion has built up layers of increasingly heavy elements. Hydrogen fuses to helium, helium to carbon, carbon to oxygen, oxygen to silicon, and finally silicon to iron. Each fusion stage releases less energy than the previous one, like a fire burning through progressively damper wood. When the core starts producing iron, the star's fate is sealed. Iron cannot fuse to release energy. It can only absorb it. The nuclear furnace that has supported the star for millions of years suddenly becomes an energy sink.